Welcome all of you. In the last class we have been discussing last couple of classes about product operators, which using that we know how to analyze a given pulse sequence. Of course, I discussed and I said the product operator formalism is developed on density operator theory, and we wanted to know how the density operator evolves as a function of time, that is we call as rho of t, and rho of 0 is the initial density operator. If I know that, then I can find out rho of t by a simple expression e to the power of minus I h of t rho of 0 e to the power of I h of t, where h is Hamiltonian, rho 0 is the initial density operator. And then we worked out lots of examples, and also the norms for working out how the free precision, how the magnetization evolves during free precision, how it evolves during chemical shift and J coupling. And we took the simple example of, let us say, one pulse acquisition, spin echo in the homonuclear case, spin echo in the heteronuclear case, and I showed the spin echo case example where by a vectorial diagram how what we understood can be explained in a simple terms using product operators. And for that we also introduce what are called the rotations operator, product operator rotations. What happens to that when we apply a pi by 2 pulse along x axis or y axis or z axis? Let us say what is the product operator Ix will do, what Iy will do, etc. And I said Ix is nothing but the rotation about x axis, Iy is the rotation about y axis, etc. And I also said there are three diagrams about what happens to this product operator when you rotate about a particular axis, x axis, y axis or z axis, and the diagram tells you what will be the next product operator when it undergoes rotation about a particular axis. From the diagram we could understand and write, in case, let us say, if there is a rotation around z axis during free position, then we know we discuss about a general formula. Always when you want to implement it using the diagram, it is like cosine of the old operator plus sine of the new operator is the general way we have to write the outcome of that rotation. And as I also said, one more important thing, the time ordering of the pulse sequence will remain same. You have to go from left to right. Let us say first RF pulse, then the delay, another pulse, another delay, whatever it is, the sequence has to be followed. But let us say during the delay, in the block period of a certain delay, there is free precision, chemical shift evolution and J coupling evolution, both would be there. I said you can take in any order, it is immaterial. And when you are applying the RF pulse, you can assume that chemical shift and J couplings are switched off temporarily, and then subsequently you can think of during the free precision time how chemical shift evolves and J coupling evolves independently. In the order does not matter, whatever the order you want. And I also said when you apply a hard pulse, let us say if you have two spin system, you can treat them as cascade of two spins, one applying on spin 1, other applying on spin 2, you can individually work it out. That is also what we discussed. We took several examples and finally we understood how using these product operators we can analyze a given pulse sequence. At the end we also understood, of course, when we brought in, first we started with a single pulse where no coupling, and we ignored relaxation during the pulses and the delay and after and later also during the free precision time. But when we took the example of two coupled spins, we brought in coupling constants. Then we introduced product operators for individual spins, for example E1, I1x, I1y, I1z, and then similarly for another spin E2, I1x, I1y, I1z, I mean I2x, I2y, I2z. Then when J coupling is taken into account, then you have to take the product of each of them, and we worked out there are 4 into 4, 16 product operators when we have two coupled spins. And we also understood one important thing in such cases, the J coupling from the in phase magnetization, because of the J coupling, goes to anti phase magnetization, and This is the one which is responsible for the transfer of polarization from one spin to other spin. This is what we explicitly understood. And in the last example of inept, we also saw how the polarization transfer takes place in the heteronuclear case. What happens if I apply 180% one spin, let us say I spin, or another spin S spin, or what happens if I apply 180% both the spins during the echo sequence. And we came to know whether which one will evolve, whether chemical shift will evolve or coupling will evolve in each of the sequences. So this is what we understood, and with this we could understand many of the 1D pulse sequences, and we understood a lot of phenomenon, interpreted the NMR spectra, everything. But now from today we will jump into a new concept, new idea, new discussion of a new topic called two-dimensional NMR. That is what we are going to discuss from today. Now in the two-dimensional NMR, when I am discussing what is that 2D will do and what is the advantage of two-dimensional NMR over one-dimensional NMR, that is what you have to understand. And first of all, the limitation of the one-dimensional NMR is the size of the molecule. If you go to a bigger molecule, like let us say a big protein consisting of several amino acids, or a big polypeptide consisting of several amino acids, in which case the number of transitions that you are going to see in the proton NMR spectrum in a given range of 0 to 10 ppm will be enormous. Because of various interactions present, chemical shifts of individual protons, and many of them are interacting with others. There is a J coupling interaction. As a consequence, there are multiple series of the transitions. And the spectrum will be enormously complex to analyze. So size of the molecule, as it increases, 1D there is a limitation. Similarly, assignment problem due to spectral complexity. As I said, when there are n number of spins present, let us say when I have several chemical inequivalent protons, if I want to take the NMR spectrum of that in the 0 to 10 ppm range, you will have lots of spectral complexity. There so many peaks are overlapped, it is very complex to analyze. And assigning each proton, particular peak to a particular proton is going to be a challenging task. And at the same time, if I want to separate the interaction of chemical shift and the J coupling from a one-dimensional NMR, it is not possible. Of course, we can do selective decoupling and everything and find out which is coupled to which, etc. But I want to separate both the interactions independently. I want to get only J coupling information and I want to get only chemical shift information separated out in one-dimensional NMR is not easy. Okay, so we need to go for 2D for that. And of course, if I want to do the correlation of one information with respect to other, let us say in a given molecule there is one proton, it is coupled to another proton, and I want to know whether which is coupled to X proton, X, Y or Z. I have to do n number of experiments of decoupling, hit at one of the proton and see the change in the spectrum in the 1D NMR spectrum. It is a very cumbersome experiment. You have to do n number of decoupling experiment to identify these things, and you cannot correlate which is coupled to which like that. So such type of things are not possible in 1D in a straightforward way. So we need to go for a higher dimension for that. And forbidden transitions, for example, we have been discussing, of course we will discuss after this study multiple quantum in detail. These transitions other than plus or minus 1, delta m equal to plus or minus 1, change in the magnetic quantum number between two energy states, if it is other than plus 1 or minus 1, they are all forbidden transitions in NMR and cannot be detected. That is what I was telling. But there is a way we can detect indirectly. For that, it is again 1D NMR is not possible. We have to go to higher dimensions. And then simultaneous detection of different nuclei. If I am doing 1D NMR, I can detect only proton at any given instant of time, or I can detect only carbon 13. Okay, another RF channel, if it is there, I can do some selective decoupling or broadband decoupling. But I cannot detect both nuclei or 2 or 3 nuclei simultaneously. It is not possible. So in which case we need to go for higher dimensions. So these are the limitations of 1D. How 2D will overcome some of these problems, we look at it as we go ahead. First, start with a simple 1D NMR which we have been discussing since several weeks. 1D NMR, one dimensional simple 1 pulse experiment, apply a 90-degree pulse with a given delay for a dead time delay, start acquiring the signal. This is called free induction decay. That is what we knew. We have been discussing, I do not need to go in detail. And I am going to collect the signal as a function of time here. And then I will do the Fourier transformation. Then I am going to get the frequency domain spectrum like this. Some spectrum, I mean, it is not need not be for this same FID, but some other spectra I am showing. So what essentially it means, time will be converted to, time domain signal will be converted to frequency domain. This is what we discussed when we discuss Fourier series, Fourier transform, etc. And in this one dimensional spectrum, there is chemical shift along this axis or frequency and the intensity along this axis. But still it is called a one dimensional spectrum. Why I am going to tell you later. And basically, before applying any pulse, we need to ensure that spins attain thermal equilibrium. That is called a relaxation delay, relaxation time we have to give. And this period is called a preparation period. So I will allow the spins to relax and attain thermal equilibrium before application of the RF pulse. That is called a relaxation delay. And then this is the time period under which I am going to collect the signal is called detection period here. This is the detection period. Okay. So this is what I am going to detect. 1D NMR basically is what from this diagram what you will understand is 1D NMR is something, the signal is collected in one time domain. Here see signal is collected only in one time domain, and you do the Fourier transformation to get the frequency domain spectrum. One domain Fourier time domain and you get frequency domain signal. That is a simple 1D NMR. What is a 2-dimensional NMR? The general pulse sequence for a 2-dimensional NMR is given like this. We have preparation period like we had in 1D, and we have a detection period where you collect the FID in 1D. That is, these two are common both for 1D and 2D. In between we have brought in two things, two periods. One is called the evolution period, other is called a mixing period. So this is a constant time detection period. We collect the FID in a conventional way like we do in 1D NMR. And this is a mixing which is optional time which depending upon the type of experiment that we as we go ahead with a particular 2D experiment we will discuss. And the evolution time is a time which is incremented. That is, we want to see as time is incremented, T1 period incremented systematically, we will understand how the magnetization evolves as a function of time. So this is called evolution period. So now we have two time periods, remember. Here as usual we allow the spins to attain thermal equilibrium, then we apply a radio frequency pulse P1, then allow the spins additional time period which is varied systematically, and we allow the spins to evolve under different Hamiltonian what we want to detect, and then mixing period is optional. Here what happens, information from one spin is relayed to other spin. There is polarization transfer takes place or some information gets transferred. And the last period is the detection period, and then we apply another pulse, it is a detection pulse, and then start collecting the signal in a conventional one dimensional way. Okay? This is called detection period T2. And this is basically is a 2-dimensional general pulse sequence. Now over the years there are hundreds and hundreds of pulse sequences have been designed to extract a particular information in a 2-dimensional NMR. So there are number of 2-dimensional NMR pulse sequences, but overall we can understand any 2D pulse sequence generally has this type of broadly 4 periods: preparation period, evolution period, mixing period and detection period. Okay. Now how do you acquire a 2D data then? In the 1D it is simple, apply a radio frequency pulse, collect the signal. Then how do you acquire 2D data, 2-dimensional data in 2 time periods T1 and T2? What we do is start like this. Assume we will start, there is a preparation period and there is an evolution period here. What we will do is initially we make the time delay between evolution time is 0, there is no delay at all. Immediately after preparation period, we have mixing period, start collecting the signal. Then I am going to give a delay, little delay, and then T1 incremented, another delay, like that I keep on incrementing the delay. You see every time I increment the delay and now T1 period is increasing, and then finally we are collecting this part, we are collecting the signal in the T2 dimension. So essentially we are incrementing the T1 as a function, T1 is systematically incremented, and for each T1 period we collect the signal in the T2 period. Okay, that is constant. Now what is happening in the T1 period? We will understand that. So this is the way 2D data is acquired. But now pictorially if you look at it, it looks like this. This is the preparation period with pulses or delay, whatever you want, keep it constant for the spins to attain thermal equilibrium. The evolution time, as you are incrementing the time, you see it looks as if how your time period FIDP is getting incremented. The time period is getting incremented. And this is a readout pulse, detection pulse or a mixing pulse, whatever you apply, and the FID is collected in the time domain here. This is a constant FID, constant period T2. Here mixing time is absent, but sometimes you can say second pulse you apply for detection, that is also a mixing pulse. So that is whatever you want you can also call, there is no problem at all. So now 1D signal in the T2 dimension after each T1 looks like this. This is the 1D FID for each T1 in the T2 period. Now in the T1 period what is happening is, as I keep on collecting the signal, let us say I do the Fourier transformation in each T1 period, I get a spectrum for one delay and I get a spectrum for another delay. As I keep on incrementing the T1, I get the spectrum like this. Now you can see that intensity is positive here, becomes mixed phase, goes negative, again come back. So it creates an oscillatory function, undergoes oscillation, intensity. See, that is the important thing. Intensity is oscillating and behaving like a free induction decay. So what you are trying to do is, you are incrementing the time, you are artificially a pseudo FID you are creating, indirectly you are creating a FID. And how many such points you will have? Typically 128 to 512, you have enormous memory, you can increment the T1 points even more, that is up to your choice. So basically we increment the T1 period, for every T1 period you collect this time domain data in the T2 period, and as a function of T1, every T1 point you measure the intensity and follow the path, it appears as if you are creating a pseudo FID. Okay. So now if you visualize the FID in the T1 dimension, it will look like that. For each T1 period, if you collect the signal and do the Fourier transformation, you get a series of FID like this. That is what we saw in the previous slide. So now take the top point of each of them, see, goes like this. Is it not an oscillatory function? It is like a free induction decay. And as T1 becomes enormously large, there will be a decay in the signal. So there will be exponential decay here also. There is enormous decay in the signal. So it behaves like a FID, exponential decay. Okay. So here T2 period is constant, but only T1 is incremented here, you see, in this direction. So now if you see the phase of the signal, systematically it undergoes change as a function of T1, and now take a particular signal for each T1 experiment, measure its intensity and plot the graph, and then you are going to get an interferogram like this here. You get an interferogram. This is another time domain signal you have created, analogous to what we get in T2 dimension. That is a constant period, it is a varied period. In this T1 period we have varied, but created an interferogram like this. This is how FID is created in the T1 dimension. Okay. So it is like creating a pseudo FID in the T1 dimension, please remember that. So now we can come to a general conclusion. In the one dimensional NMR, we had a single time domain data. I did a single Fourier transformation and I get a single frequency domain spectrum. That is correct, right? Now in the two dimensional data, we have two time periods. We have to do double Fourier transformation, because we have two time periods, we get two frequency domain spectra. Okay. So two dimensional data, you have two time domain data, two time periods, two time domain data otherwise, and you do the double Fourier transformation, you get two frequency domain spectra. Okay. So this is how double Fourier transformation of a 2D data looks like. For example, I have collected, let us say, data in both T1 and T2 like this. I keep on incrementing, T2 is constant, T1 I am incrementing and collecting the data like this. Okay. I have done the experiment, collected the time domain data both in the T2 period and T1 period. I will do the Fourier transformation. Now the Fourier transformation, which dimension I am doing? In the constant period T2. So now in the T2 is the time domain period. After doing Fourier transformation, it became omega 2. It is a frequency now in this dimension. But still in this dimension it is still a time period, because I have not varied, I have not done the Fourier transformation. Now again I will do the Fourier transformation in this dimension also. Now I have frequency domain here in the omega 2 dimension, frequency in the omega 1 dimension. The spectrum now looks like this. The time domain data became frequency domain data in 2 dimensions now. You can have the frequency you can measure from this dimension, you can also measure the frequency of this in this dimension. So depending upon where you get the peak and what type of experiment you do, the two-dimensional data after double Fourier transformation, you get a frequency domain spectrum that contains lot of information. Okay. So, it gives frequency spectrum in 2 dimension by doing double Fourier transformation. This is how it works. You understand? Now, about higher dimension. Can we go even higher? We discussed about 2D. Can I go to 3D? Can I have 3-dimensional data, 4-dimension, 5-dimension, n dimension? Why not? It is possible. But only thing within the limit of complete decay of the signal, before it completely relaxes, you have to acquire all the data. So, there is a time limitation as far as the relaxation is concerned also. But you can have n-dimensional data. We will consider how we represent the 2D and 1D, 3D, etc. in the higher dimension of NMR. First, apply an 90-degree pulse, collect a signal, it is 1D. This is a one-time domain. Now, I can have 2-dimensional data, it can be different nuclei, it can be heteronuclear, it can be even homonuclear also, no problem. You can have one pulses, you can apply selective pulsar, hard pulsar, whatever it is on one channel. You can apply another pulse on other channel. And then you can collect the T1 in the X nuclei, you can collect this signal in the proton channel. So, you can collect the signal in the T1 dimension in the X nuclei channel or in the T2 dimension in the proton channel. Either of them is possible. So, you can collect time domain data in 2 channels for 2 nuclei. That is what I said. What is restricted in the 1D, it is possible here. Using 2D data, you can selectively detect 2 nuclei, or even 3D if you go to 3 nuclei if you go to 3D. It is possible. Okay. This is how we collect 2D data for 2 different nuclei. Now, this is 2 dimensions. What is 3D NMR then? Can I go to 3D, 3-dimensional? Of course, yes. Then we can have 3 different nuclei, carbon 13, nitrogen 15 and proton. You apply a pulse on proton, carbon 13, collect the FID, this is one period. Then nitrogen you apply a couple of pulses and do something for nitrogen spins and collect signal here, that is T2. Then in the last period T1, last T2, this is T3 period here, T1, T2 and T3. This may be on the proton channel and collect the signal. Finally, you have to collect the signal in one of the channels. Proton channel is collected here because it is highly sensitive. So, we have 3 different nuclei and 3 different time periods, it is 3D NMR. You have to do Fourier transformation in each time period. You get frequency in 3 dimensions. It is a 3-dimensional NMR spectrum. Okay. So, this is what it is, 3 dimensions are highlighted here, 3 time periods and 3-dimensional NMR. So, now question is, what defines the dimensionality of NMR? A pulse sequence containing n time period gives n-dimensional NMR spectrum. Remember, a pulse sequence containing n time periods gives like T1, T2, T3. Previously we saw for 3D, 3 time periods T1, T2, T3 were there. You can have more T4, T5, T6, no problem. Depending upon number of time periods, you get that many dimensional NMR spectra. So, for 3 time periods you get 3D spectrum, for 4 time periods you get 4D spectrum. So, you can have 2D, 3D, 4D, ND spectrum, that is possible. Okay. So, another important point you should remember is, if I have n time periods, n-1 time periods are varied generally. Of course, if you want you can keep one of them constant, or that is special experiments, you can have n number of experiments. But generally, if I have n time periods, n-1 periods are varied, and the detection of the last period is always a constant, that is called detection period. I am sorry, duration of the last period is always a constant, that is called the detection period. You understand? In the n period, n-1 periods are varied, last period is the period in which you detect the signal, that is a constant period called a detection period. In each time incremented, you will increment this in the time is incremented in the other dimension, and you create pseudo FIDs like we observed in the 2D. In each of them you have to increment the T1 and then create pseudo FIDs and do that many number of Fourier transformation of the time domain signal, you get that many number of frequency domain spectrum. Okay. So, we can have generalize like this. If I have a pulse sequence with n time periods, I design a pulse sequence. Homo or heteronuclear doesn't matter. N time periods are there. One is fixed and n minus 1 I vary and create n dimensional time domain data. If pulse sequence with n time periods gives n dimensional time domain data and do the Fourier transformation, you get n dimensional Fourier transformation you have to do and you get n dimensional frequency domain spectrum. Please understand, you get n dimensional frequency domain spectrum when you do n dimensional Fourier transformation. That is important. You understand? So then we call this as NDNMR. N dimensional time domain data, n dimensional Fourier transformation gives n dimensional frequency spectrum called NDNMR. Okay, now illustration of a two dimensional spectrum. How do we illustrate the two dimensional spectrum? Basically, there are various ways of defining, various ways of having a 2D spectrum. Now over the years, NMR spectroscopy has advanced so much. You have n number of experiments to derive information, and each time you can have a different information in different dimensions. But basically, broadly speaking, I will say there are two types of experiment we can think of. One is the resolved spectrum, where the two informations are resolved in two dimensions, are separated out in two dimensions. In one dimension you can have a frequency, other dimension you can have a J coupling. That means you can have a chemical shift here, you can have J coupling here. J coupling and chemical shift will be present in the 1D spectrum, both will be present. They are inseparable. But in this two dimensional NMR, you can separate out both of them in two dimensions. That is called resolved spectrum. You are resolving two information, two parameters of NMR. Otherwise, we also have correlated spectrum. In the sense, I can correlate information from one part of the molecule to other part. For example, there is a big molecule, I have a proton here and I have a proton here. I can correlate how it is coupled to this. I can correlate the information from one of these spins to with other spin. This is called correlated spectrum. So there are two ways. You can have a resolved spectrum and you can have a correlated spectrum. Both are possible. Okay. So how do you represent the time domain data? Very good old days, long back, even probably even when I was young, they used to have a stack plot where it used to be plotted like this. Now it is no more done, it is completely done away with. The representation of the 2D data is only a contour. It represents this, each of this peak is represented in the form of a contour here. This is a spectrum actually, it is a peak. It is represented in the form of a contour plot. So this type of stack plot is almost done away with, or more, it is done away with. Nobody is going to use that nowadays. Okay, always contour plot. Then you may ask me a question, what do this contour, how does contour is represented when there is a peak like this? How do we call it a contour? How it is represented? How do you translate peak into a contour? It is simple. I am going to take a let us say I am going into like a mountain. I go to the bottom of the mountain, go one round, take the area and put a circle. And I go further up, go round, get the area, put one circle. Go further up, put area like this. Each time I keep on going at different heights, go round, take the area and then put a circle. So that means essentially this contour area gives you the area of the peak. That is the way the contour is represented and translated into, peak is represented into contours. So this is what happens. You have different areas, go up and up and up. Every time you go up here like this, go up here, measure this area, put a circle here, and go up, measure the area, put a corresponding to that another contour, another circle like that. Keep on stacking one after the other here. The same stack plot is now translated into the contour here. This is a translation of stack plots into contour plots. Okay. So area of the contour, that means if I get the area of the contour in the 2D spectrum, it means I am getting the integral area of this peak. That is what. It is just translation of the integral area of this peak into area of the contour. It is represented instead of peak as a contour here. That is all. That is how that peak is translated into contours. Now let us discuss about the time constraint in higher dimensions. If I am trying to go to higher and higher dimensions, is it easy? Is it possible for us to go to all higher dimensions whenever we want or whatever the molecule we have. It's not, I think there is always a time constraint. For example, here is a plot about measurement time or the dimensionality of the NMR. If I go to 1D NMR, normally if I want to do the proton NMR for a small molecule or even a reasonably big molecule which do not have abnormally large long relaxation times, you can get the NMR spectrum of, let us say, proton spectrum of such molecule in less than 5 minutes nowadays. Okay, very fast. You go to 2-dimensional NMR, how much time it takes? You have to acquire the data in 2 dimensions, like fixed time and vary the time. Every time you have to acquire the data, it is time consuming, no problem. 2-dimensional data definitely takes more time than 1D NMR data, time domain data. How much time it takes? Now in the present day methodology, it is also rapidity is there in the acquisition, everything. You can say it is also of the order of few minutes, make 30 minutes to half an hour to 1 hour, like that, no problem. That is also still faster. You go to 3D NMR, it can go up to hours. Go to 4D NMR, it can go to days. If you want to take 5D NMR, you may have to spend weeks to acquire the data. It is not easy. You have to consume enormous amount of the instrument time. The measurement time increases exponentially with increasing dimension, increase in dimensionality. Further, the sensitivity also goes by root of measurement time, that you should understand. We discussed in the very first course about signal to noise ratio, everything. How many times you have to acquire the signal to get the S by N of root of n, all those things we discussed, right? So it also goes by measurement time. And now dimensionality of NMR, and it also depends upon the size of the molecule you are looking at. It is not that you take a simple molecule like a water and you want to go to take the higher dimensional NMR, or want to go to higher frequency. These are all not needed. You have to judiciously decide which type of spectrometer you require, what frequency, and what is the type of molecule, whether you want 1D NMR, 2D NMR, 3D NMR. That depends upon the complexity or depends upon the size of the molecule. If I take just benzene and you get 100 megahertz, 50 megahertz, 60 megahertz is sufficient. You get a single peak. You don't have to go to 800 megahertz, or you don't have to do 2D NMR. So dimensionality and the frequency which you want to choose for doing the experiment all depends upon the molecular size and spectral complexity. If I want to take a 2D NMR, generally you have to go to molecular size becomes higher and higher, molecular weight becomes more. See, you can go up to 0 to 20 kilodalton. We are taking the example of proteins here. Then you can up to 0 to 20, let us say, you can go to 2D NMR. Reasonably okay. Around that 20 to 30, if you go, even 3D will do. 4D, you can go up to 40 kilodalton, like that. Higher, if you go up to more than 40, up to 80 to 100 kilohertz, under 100 kilodalton, you need 4D NMR and even higher experiments, other special experiments you require. So dimensionality increases with the size of the molecule. Okay. So the increased information and the resolution is with increased dimensionality. Okay. As you go to higher dimension, you have increased information and you can have a better resolution. In the sense, you are resolving the information or spreading the information in different dimensions. Okay. And as you increase the dimension, these two parameters benefits you. Okay. And if you go to I will go to the benefits of higher dimension, and then we will it will take more time to explain. Okay, now the time is up. What I am going to do is I will stop here and we will come back and continue with this from next class. But today what I wanted to tell you is I started introducing the 2D NMR. It is another dimension of NMR which was introduced way back in 1971 after the first genus experiment, and Professor Richard Anderson is the one who is pioneered this type of technique and who got Nobel Prize. He is the one authority of this 2D NMR. He was responsible for the development of this technique and introduction of this type of techniques. And nowadays there are n number of such type of multi-dimensional experiments, both homonuclear and heteronuclears have been designed by various workers in the field. And what is happening is one dimensional NMR, I said, you apply a pulse and collect the signal in a time domain, one time domain, you do the Fourier transformation, you get one dimensional spectrum. In the two dimensional, on the other hand, I said there are 4 time periods: preparation period, evolution period, mixing period and detection period. Of course, mixing period is always optional, that depends. Sometimes even a 2 pulse experiment, the second pulse itself can be treated as a mixing pulse, that is okay. So 4 time periods are there. Preparation period is to allow the spirits to attain thermal equilibrium. Evolution period is the one where we increment the time systematically Every time we increment the signal time, we collect the signal in the T2 dimension. Now as a function of time, we create a pseudo free induction decay in the evolution period. Now we have time domain data in two time periods. Do the double Fourier transformation, you get it, 2 frequency domain spectrum. And always if you have n dimensional spectrum, you have n time periods, n minus 1 periods are varied, 1 period is kept constant. So n time periods, n dimensional Fourier transformation, you get ND spectrum. And I said it also depends upon the time. As you go to higher and higher dimension, enormous amount of time is going to be consumed. For example, I said 2 dimensional NMR, you will start with few minutes, 3D NMR few hours, 4D NMR few days, and if you go to 5D NMR etc., you will go to several weeks of acquisition of the data. Instrument time will be consumed enormously. And also I said it depends upon the molecular size. For small 1D NMR, small molecule, you can get spectrum in 5 minutes, or if you go to 2D NMR, you can go up to molecular weight of 0 to 20 kilodaltons, and for 3D NMR slightly more, you can go up to 40, and above 40 to 50 or 60 you can go to 4D NMR. If you go to even higher molecular size of protein, above 50 or 40 kilodaltons, you may have to go to 4D NMR with another special experiment. So increased information you get with increased resolution as you go to increased dimensionality. So this is what we understood today. I am going to stop here, we will come back and continue with the 2D NMR in the next class. Thank you.